I'm pleased to introduce Souradip Ghosh, who did his practicum at the Pacific Northwest National Laboratory and is studying computer science at Carnegie Mellon University.
Thank you. So today I'll be talking about asynchronous programming for spatial data flow architectures. This is some of the recent work that I've been doing with folks at Carnegie Mellon, where we work on energy-efficient computer architectures. And so to give you some context about where this line of work is coming from, we started looking for open problems with the huge proliferation of sensor devices that have been coming forward in recent years. And so these are some of the examples of applications and devices that we've looked at in our labs, including nanosatellites, wearables, wildlife monitoring that's used in agriculture, and many more. And ARM claims that there's going to be trillions of these devices in the future. Probably not that many, but the point here is there's going to be many different kinds of devices, many different kinds of complex applications that these devices need to run. And so with all of this going on, this kind of begs for multi-year device deployment. It's really not sustainable to think about all of these applications and devices if we need to replace a device every few months, or if we need to replace batteries every few weeks or something like that. And so this has two implications. We need compute that is both efficient, so that we can run our device on a commodity AA battery for a very long time, and it needs to be flexible. We need to have one kind of computer architecture that can run in many different kinds of applications. And prior work has also determined that we need to run as much of that computation on device in the field as much as possible, because communication from the device back to some server that's going to process something takes a lot of energy, and it's going to drain your battery. So that begs the question, which architecture is both flexible and efficient? So you can think about it in terms of this trade-off space. I've got a little graph here. And on the one hand, we have conventional CPUs, the stuff that's in your phone, stuff that's in a microcontroller. And they're very flexible, but they're very inefficient. And upwards of 90% of the energy on conventional CPUs are wasted by doing non-compute, fetch and decode of instructions, the register file, etc. On the other hand, we have ASICs, or application-specific integrated circuits, where the point here is you want to accelerate one kind of application. So it's inflexible by design, so it doesn't address the flexibility criteria. But in the middle, we have this thing called a spatial data flow architecture. And this is where my research is focused on. And so these are programmable with software, but they use a different kind of execution model in hardware completely. Instructions of the same thread or a program are distributed across processing elements across the actual chip. They're communicating directly to each other. They have an asynchronous execution model. And so there's a lot of benefits because we can get rid of the inefficiencies of a CPU while still maintaining high performance. So this is kind of balancing energy and flexibility. And so early on in my PhD, we really tried to push the boundaries for SDAs so that we can make them more flexible and more energy efficient. And so that led us to the first project that I worked on, which is called Riptide, which tried to accomplish this. And so when we looked at sensor devices and spatial data flow architectures that addressed this problem, we found that there were many. They were super energy efficient, except that they only accelerated a very small portion of the program. And so in Riptide, we identified that this is an Amdahl's law bottleneck. The end-to-end energy savings or performance of the whole device is limited by how much you're actually going to accelerate. And so for Riptide, we thought, let's just try and accelerate everything. So that's what we did. We built an energy minimal spatial data flow architecture that accelerates any kind of C program. It runs entire C programs. We built a compiler, the architecture, a lot of energy efficient hardware that's built into it. This is a slice of that architecture. Each of the colored squares in the middle are processing elements. They run in individual instructions, and they're connected through routers in a network. And other students in the lab ended up taping out this chip and fabricating it as well. And so we got some energy numbers, and on a tiny ML-style DNN, or deep neural network, compared to something that's off the shelf, we got something like 1,900 times energy savings compared to those commodity devices. So this is fantastic. So we've addressed flexibility, we've addressed energy efficiency. We are missing the performance aspect of things. And so we can think about performance if we take a look at this makeshift ternary plot. And so we have flexibility, energy efficiency, but now we've added performance to this. And so on the one end, we have CPUs. They can run anything. On the other end, we have GPUs. They're very high performance. ASICs are high performance and high energy efficiency for one application. And Riptide, which is abbreviated RT here, is somewhere off to the side. It's doing flexible compute. It's doing energy efficient compute. But it's missing this part of the plot. And so this kicked off a whole line of work in our lab that I've been a part of. And I've gotten to work on a lot of these projects that are focusing on addressing the performance aspect of things in addition to energy efficient compute. And we have a few papers here, and in addition to that, we have a startup called Efficient that's commercializing some of this work. And so for the rest of this talk, I'm going to give you some details about Ripple, which is one of my recent projects, where we worked on asynchronous programming for these spatial data flow architectures. And so to kind of talk about Ripple in a nutshell before we dive into some of the details, the way that this work came about is we saw that SDAs like Riptide were really good at accelerating things like a deep neural network, something dense, something very regular. But if we looked at something that was more complex, it had irregularity, it had to do complex control flow or arbitrary memory access, the code would become bloated and the performance would be slow to the point where it might not fit on the architecture itself. And so something like this, we have a graph traversal. Our insight was that these kinds of applications express coarse-grained data flow behavior, where we could actually categorize the applications such that we can think about them as regions of code that are communicating data to each other asynchronously. And so this is nice because an SDA actually has this model built into it. It's asynchronous, it has queuing, it has things like pipelines, and so the hardware should be a good fit for these kinds of applications. But the problem is the software, unfortunately. And really the issue is a lot of these applications are written with low-level code like C, where it compiles down to low-level memory and control flow operations, and we've destroyed all of the nice data flow behavior that we had in the application that's modeled by the hardware. And so that graph application that I showed you earlier has a program representation that looks like this, which is very complicated. And so this does not fit on a standard spatial data flow architecture. It's very bloated and it's very slow. And so this we call as an abstraction inversion. So we have a model of the hardware that's doing data flow. We have a model of the application that's doing data flow. And the software kind of loses all of that information when we compile it down to the hardware. And so our solution here was we want to just expose the asynchronous data flow semantics of the spatial data flow hardware directly in the language. And so Ripple does this. So it's a language and an architecture that corrects this abstraction inversion. And so what we've done is we've built in an asynchronous parallel programming language with many of the features that a spatial data flow architecture already exhibits. We've expanded the instruction set architecture, or ISA, so that the compiler can take that knowledge of the language and compile it down very efficiently, almost one-to-one to primitives that already exist in the hardware. And so that graph application is much more compact if we write it down with Ripple. And so this is what it looks like. These are instructions. They're communicating to each other. It's much more compact, much faster as well. And so we compared against Riptide, and we found that across a bunch of applications, like graph applications, stencils, and whatnot, it's 3 times faster on average, and it halves the program size, which is good. So I want to give some intuition about how spatial data flow architectures work before I dive into some of the details. And so I want to start off by how we represent programs and what the architecture looks like. So if we have some code, this is very, very simple. What we'll do is we'll compile a data flow graph, or DFG, of instructions. And we don't have a sequence of instructions like a CPU has. These are dependent, and so they're communicating to each other. And these are represented and mapped onto a spatial data flow fabric, where each instruction is mapped onto a PE, or processing element, and they communicate directly to each other. And so we have PEs here. We have a network with, that's abbreviated with R all around it. And if we zoom in a little bit, we'll see that each PE has these queues that are managing all the inputs to of all the instructions that are communicating to each other. And this is super important because this communication is the key to handling all of the energy efficient components of the SDA. We don't need something like a register file, we don't need fetch and decode. Data values can just flow through these hardware queues and everything is managed automatically. And so this is an important point to keep in mind for later. And so if we want to run a program on a spatial data flow architecture, we have data flow execution. And so in this case, instructions can fire asynchronously because inputs can arrive asynchronously, and then they can just go. So like in this case, the multiply receives its inputs, it can just fire whenever. Hardware queues are managing this automatically, and so the software doesn't have to do anything to flow tokens through instructions. And so the last piece that I want to talk about in terms of basics is how, in the best case, SDAs can achieve high levels of pipelining. So in this diagram, what I'll show is a little bit of code, a simple pipeline, and I want to walk through what's going on in each step. So this is a data flow graph of instructions, and what we've done is we're starting with the for loop at the top. We fired I equals 0, I equals 1, and what you're seeing is tokens are flowing through and more instructions are ready to fire, and we're pipelining loop iterations. And so this is really good because the more dense this pipeline diagram looks, that means the more pipelining we have, the more parallelism we have. So this is good. This is what we want to see in the best case for all the applications. Now, unfortunately, there are applications where this is a problem. So BFS, or breadth first search, is one. And so to give just a little bit of a primer on BFS, we can have an input graph, and we're going to build a search tree, which is represented by this parents array. And we'll have some outstanding work along the way as we queue things and we search more of the graph. And so the way this works is we can pick a vertex, we can iterate through its neighbors, we can filter for the unvisited ones, and we can write to parents, recording the search. And the outstanding work is handled by the work queue here in the middle. And so we just do this until it's done. And so SDA should be great at this because we can have continuous flow of tokens, or in this case, vertices, through the entire graph. And this is exactly what we want on a data flow architecture where there's good pipelining. In particular, even, the work queue should be handled really easily by a hardware queue, because that's exactly what the hardware queue is doing. It's automatic, and whatever's in the application has a good representation in the hardware. But unfortunately, a lot of these programs are not handled well by SDAs. So the list of papers that went off on the right here are examples of SDAs that use C or CPU-like assembly to program their hardware. C lacks abstraction for data flow semantics, and so we can't represent this code well. And so this manifests in a few ways. First, the code itself. Instead of programming a hardware queue, we have a software queue that's written using memory operations to implement asynchronous communications. So now I have a lot of instructions. And then we have an irregular while loop instead of an automated pipeline that's handling the pipeline of vertices going through the program. And so this is the abstraction inversion that I was talking about earlier. We had the hardware queue. We had something that's queue-like communication in the application, but we've written it down using low-level operations. And so this manifests with bad performance as well. So I kind of want to show a pipeline diagram of this. And so in the best case, I've listed out some of the instructions that are important. In the best case, we want to pop a vertex, iterate through its neighbors, set the unvisited parents as quickly as possible. And so we're pipelining loop iterations here. And we can do the same thing as we find new vertices. But unfortunately, that doesn't happen if we compile with C. And so we have a lot of this bloat, we have low performance, and we have these red arcs here. And this is memory ordering. And so with memory ordering, what happens is we end up serializing the iterations because there's a race between like read after write operations across loop iterations. And so this happens for parents. This also happens for push and pop. And the way that the compiler handles this is we add a bunch of control flow to handle all of the memory ordering so that we serialize all the loop iterations. And so if we look at this here, we have to finish one pop, all of that entire first while loop iteration, before we can start another entire iteration at the right side. And so we get this graph that looks like this, so that we've seen before. So the bold bordered red nodes are all the ordering, so this is the stuff on the right, in addition to all the extra instructions that we needed for the software queue. And so this is so big that it might not fit on the architecture. So what Ripple does about this, and it's a language and an ISA that targets spatial data flow architectures. And our goal here is we're going to take this work queue and we're going to map it directly to a hardware queue here with a one-to-one lowering. And so, I'm running out of time here. So what we'll do is we'll get rid of all of the software queuing and we'll replace it with asynchronous regions. And so we have one here that's handling init, and we have one here that's handling the rest of the code. And so users are going to write asyncs that distribute this code around. And so give an idea of how this works. An async here has a name, an input, and a body. It defines a queue. And those inputs arrive asynchronously. And so those tasks will launch, tasks are each iteration. They launch immediately and automatically. And then we have push here, which defines the communication to its async. So we have something that looks like the automated pipeline that we wanted to see for BFS. And so this should look familiar because we have something like an async, where things are arriving asynchronously. And just like in hardware queue that's managing a PE, things can fire immediately. And so this is modeling what the hardware queue is doing. Same thing for push, because that describes the communication. I'm going to skip over this in the interest of time. But the end goal here is that we have a full program. We've added atomics. These are other details that I'll gloss over, that we can handle synchronization with and add more pipelining. If you read the paper, you can see that Ripple is deadlock free, and that's important for cyclic communication. And because we're just exposing the hardware queue using the architecture, we don't add a software runtime, and we don't add any complex hardware. The hardware is already there. We're just abstracting it differently through the language and the architecture. And so the graph here ends up looking like this. And so this is faster and simpler. If we look at a pipeline diagram, we'll see that because of atomics and because of task queuing, we can actually achieve that nice pipelining that we see, that we wanted to see in the theoretical best case. Okay, I think I am in between everybody and lunch, so I'm going to skip over the results. Just to highlight the average result, Ripple is about 3 times faster than Riptide, and it's about 14 times faster than a conventional CPU. And then I'm going to skip over that. And Ripple is able to also shrink programs by about 2 times because it eliminates a lot of the control flow based on ordering. Okay, so if we take a quick step back, we had Riptide here, and now we have Ripple in the middle. So we're breaking into that area where we want higher performance. And so this is a little bit of, I kind of want to leave it here in terms of like, we can now start to look at computer architectures by not just highlighting and really striving for performance. We can start at an energy efficient place and then work into a higher performance design. And so this might be able to inform how we do architecture design in the future, where obviously we need to balance energy, sustainability, and performance as well. Okay, and so with that, I wanted to thank especially my advisors, Brandon and Nathan, some of my longtime collaborators, and many other people and organizations that have helped me along the way. So thanks.